Hey, I wanted to put together a quick little video for instructions on 55.5. So you have it in your packet. You should have taken it out by now. And this is a piece of notebook paper, as you can tell, because I do much better with lines, and maybe some of you do as well. Here's how I would go about this assignment. I would I'd state what color or whatever, what type of wave we have, and skip at least 5 or 6 lines between. So I'm going from red, infrared to red, orange, yellow, green, and then on the back you're going to have the rest of your colors. Put them in order, work from left to right here. So this wavelength here is infrared, and so what I would do is, and I'm not going to do it on this one, the first thing I do is just to the right of this is I would figure out from the diagram what the wavelength is. Now with that wavelength, I would estimate it to the tens place and probably leave the ones place as a 0. Then I would show my conversion going from nanometers to meters, and you have to use dimensional analysis as it says. And then here you're going to be finding the frequency, and here you're going to be finding the energy. So I'm going to do one of these with you or for you, and so just pay attention. I'm going to do orange. So the first thing I have to do at orange is I have to look at my visible light spectrum, and when I look at that, I see that the orange is about halfway between, look at your diagram, it's about halfway between 580 and 700 nanometers. So that's a difference of about 120. So half of 120 is 60. So I'm going to estimate orange to be about 640. So I'm going to say estimated 640 nanometers. Now I'd like you to recognize that this is my estimated value, and this 0 is a placeholder. So I have two significant figures here. So if you estimate consistently to this tens place, you're always going to be using two significant figures. Don't make your life difficult by saying, oh, 642, because you really can't estimate all that well. So the next thing you have to do then is you have to convert from nanometers to meters. And so take your estimated value, that's your given. This is a number, this is the unit. Time sign, fraction bar. You're going to be converting from nanometers to meters. And so I have it written up top here, and you probably would want to write all this stuff down when you have a chance. If I have 1 meter, that's equivalent to 1 times 10 to the 9th nanometers. So once I do my math then, so this is wavelength equals, once I do my math then, I have 640 times 10 to the 0 minus 9 is negative 9th power. At that point, then what I have to do is I have to get my decimal in the correct place. Practice this with your basic calculator. If you're doing this with your graphing calculator, you are not going to do well on your test when it comes to doing this. You have to practice your exponents. So what I have to do is I have to make sure that my decimal ends up after the 6. So it's going to be 6 decimal point 4, and I'm going to stop there. The 0 is a placeholder, so this is two significant figures. But I had to move that decimal, which isn't shown here because this is a placeholder. I had to move it 2 places to the left. So my 640 became 2 powers of 10 smaller. So 2 places smaller, this means I have 2 powers of 10 larger. So this is going to be times 10 to the negative 7th meters. Okay, so that's number 2, and you might want to space things differently. Maybe you have a better way to do things as long as all of this is shown. So I need to see this. I need to see this. I need you to use dimensional analysis. I need you to use the correct amount of significant figures. I'll tell you right now, it's always going to be 2 if you estimate properly. So then you're supposed to go to 3, and you're supposed to find, for number 3, you're supposed to find your frequency. So Ms. Bryan tells you on that sheet that you're going to find frequency using C equals lambda nu. All right, now because of the amount of space and because of the length of this assignment, if you write C, speed of light, up here one time on this assignment only, then I will not make you make a list for me. Okay, it's right up here. On the back side, you might want to do that again so you don't have to keep flipping it over. So I'm going to use this equation, C equals lambda nu. Why? Well, because I have wavelength and I'm calculating frequency. But you are not going to plug into your equation like this. If you are finding your frequency, you have to divide both sides by lambda, and this is what you're going to plug into. So follow the rules, because this is why a lot of you guys lose points, because you don't follow the rules that we're teaching you. So I'm going to go ahead now, and I'm going to do this problem right here. So I'm going to have frequency equals 3.00 times 10 to the 8th meters, and I'm going to put my seconds on the bottom, meters per second, and then my lambda is going to be from over here, 6.4 times 10 to the negative 7th, has to match. That's why we converted meters. Alrighty. Now, at this point, when I do my math, I'm going to come up with something that looks like this, 0.4687, blah, blah, blah. So that's my coefficient right now. I'm going to cut the sig figs in a minute. Now I have to worry about the exponent. So you're dividing 8 minus negative 7. 8 minus negative 7, and that gives us a 15. Yes, it does. Now I have to cut this to 2 sig figs and get the decimal to the right place. So my decimal has to be after the 4, and this 6 is going to round up to a 7 because it's followed by an 8. So here we have 4.7 times 10. Watch it. Every time when you write this down, you have a lot better chance of getting it right. If you have a number as your coefficient that gets larger by a power of 10, that means this 15 has to decrease by a power of 10. All right, now units. We cross off meters, and we're left with that crazy 1 over a second, which is hertz, which is the frequency unit. Okay. What I would do, not only for myself, but for my teachers, I'd probably make sure that my answers are notated somehow, or it's easy to find them. Okay, so perhaps put little boxes around your final answer, make it easier for everybody. Okay, so then your last problem is going to be to find the energy of that wavelength. Okay, so you're going to find energy. This is going to be E equals, and I do want these basic equations stated and rearranged for everything. Planck's constant times frequency. Well, here's your frequency. You're going to be pulling from here. And then you're going to be multiplying that by Planck's constant in order to get the energy. Let me just tell you a few things here. And this is why many of you are doing so poorly on your labs. Many people are making a mistake right here. And then they're continuing that mistake. And whereas I don't keep counting off, you're making more and more mistakes. You're tailoring your significant figures wrong. You're not using them properly. Your units wrong. You flipped your conversion factor. So you just keep making one mistake after another, and you're not checking it. You're not going back and asking yourself if things make sense. All right. So one of the things you need to ask yourself is, have I done what I'm supposed to do in applying all the things that I've learned in this class on this assignment? And many students are not applying what we've learned. Okay. So ask yourself, does this make sense? You're always going to have you're always going to have an exponent that's more than 0 for the frequency. You can't really have a negative frequency. So just watch that and think about it. Okay. So now we have energy equals Planck's constant times nu. So that's going to give me E equals, and I have to multiply 6.626. You have to write it out, times 10 to negative 34th, and that's joule seconds, times this frequency from here, 4.7 times 10 to the 14th power. And that's going to be hertz, but I'm not going to put hertz. I'm going to put 1 per second, or I can put s to the negative first there. So if I go ahead and multiply, then I'm going to go ahead and cut my sig figs to 2 since I don't have a lot of space. So my sig figs, I'm going to have 2 sig figs. I'm going to get a 31. 2 sig figs here. For here, we're going to limit to 2. So I have 31. Now I deal with my exponents. I'm multiplying, so I add these together. Negative 34 plus 14 brings me up to negative 20. So it's times 10 to the negative 20th. And so I have to adjust my exponent. It has to be after the 3, decimal point, whole number there too. So we have 3.1. This value right here, my coefficient, gets smaller by 1 power of 10 from here to here. It gets smaller by 1 power of 10. If this gets smaller, this has to grow larger. And so don't forget, larger for your negative values gets closer to 0. So what you end up with here is 3.1 times 10 to the negative 19th. Your seconds cancel and you're measuring energy. So here is joules. Okay. Now, I would probably maybe skip another space here since you can see how crammed in my work is. Some of you guys write smaller and some of you write much bigger. So kind of figure out how much space you need. I want you to make sure though, when you're working on this, you have to label and go in order. Don't go all out of order. Okay. So now when you do these calculations, you may not have anticipated, or you might not have estimated rather, the wavelength the same as somebody else has. But I will tell you this, despite the fact that you might be here 630 or 650, you are still going to have the same exponential values. So keep an eye on that. You're going to see a pattern here. This is a very, very small range of wavelength. So these exponents are going to be very, very close to each other if they are not exactly all together. So look for the commonalities and you can catch your mistakes a lot easier. Okay, so I did orange for you. Recommendation, use more space. All right. Hope you do well on this assignment. Have a good break.